Hello and welcome to this video on titrations. My name is Kim, and in this video we'll be calculating the pH at different points throughout a strong acid, strong base titration. Strong acids and bases are characterized by the fact that they fully dissociate in solution. The different types of acids and bases are described in another video. With a strong acid, in this case HA, it will fully dissociate to form the conjugate base A- and the hydronium ion, and none of the initial HA will remain in solution. For the strong base, BOH, it will fully dissociate in solution to form the conjugate acid B+ and the hydroxide ion. Again, no remaining BOH will remain in solution. The presence of the hydronium ion and the hydroxide ion will affect the pH of the solution. In a strong acid, strong base titration, since hydroxide is reacting in a 1-to-1 ratio with hydrogen ions to produce water, and since there is complete dissociation to produce hydroxide and hydrogen ions, it's relatively straightforward to subtract the number of equivalents of acids and base, and the leftover moles will determine the pH of the solution. In a sense, calculating pH in a titration is a limiting reagent problem. The first step is to determine whether there are hydrogen ions or hydroxide ions left over and how many moles are left. Next, add up the total volume of acid and base. Third, divide the total moles of leftover hydrogen or hydroxide ions by the volume. Finally, use the equations to determine the pH. If hydrogen ions are left over, then use pH equals negative log of the concentration of the hydrogen ions. If hydroxides are left over, use this equation, pH equals 14 minus negative log of the concentration of the hydroxide ion. The second equation might seem new, but it's not. Since POH equals negative log of the concentration of hydroxide, and pH plus POH is 14, this seemingly new equation is essentially just putting these relationships together. Let's put this into practice with the apply question. The question stem is asking us for the pH of the solution at different time points in the titration. The unknown concentration is sodium hydroxide, of which there are 50 milliliters. The known acid that is being titrated with is 0.05 normal hydrobromic acid. The student finds that it takes 10 milliliters of hydrobromic acid to neutralize the sodium hydroxide. The first part of this question is asking for the pH at the beginning of the titration, so before any acid has been added. Well, since sodium hydroxide is a strong base, the concentration of sodium hydroxide will equal the concentration of the hydroxide ion, which is necessary to calculate the pH. However, since the concentration of the sodium hydroxide is an unknown variable, we have to calculate the concentration of base using the equation normality of acid multiplied by volume of acid equals the normality of base multiplied by volume of base. Rearrange the equation to solve for the normality of base and add in the values. The normality of sodium hydroxide is 0.01 normal. The concentration of hydroxide also equals 0.01 normal, since strong bases fully dissociate. To calculate the pH, use the equation described earlier, pH equals 14 minus negative log of the concentration of the hydroxide ion, and sub in the hydroxide ion concentration of 0.01 normal. The pH of sodium hydroxide before any hydrobromic acid has been added is 12. The second part asks for the pH of the solution when 5 milliliters of 0.05 normal hydrobromic acid has been added to 50 milliliters of sodium hydroxide. Remember the steps. Calculate the moles left over, then the total volume, then use the information in the first two steps to calculate the concentration. Finally, use the equation relating pH and the concentration of hydrogen or hydroxide to calculate the pH. Step 1. Use the definition of normality to calculate the equivalence, and this definition was covered in an earlier video. Normality is equal to the equivalence divided by the volume, so rearranged, equivalence equals normality multiplied by volume. If you consider where the student is at in this point of the titration, and if it takes 10 milliliters of hydrobromic acid to reach equivalence, then at 5 milliliters, there are definitely more hydroxides than hydrogen ions. Equivalence will equal the sodium hydroxide concentration, which is 0.01 normal, calculated in part A, multiplied by the volume of 0.05 liters. The equivalence of hydroxide is equal to 0.0005 moles. Equivalence of hydrobromic acid is 0.05 normal multiplied by the volume of 5 milliliters or 0.005 liters. The equivalence of hydrogen ions is 0.00025 moles of hydrogen ions. Subtracting the two together, we get 0.00025 moles of hydroxide ions. Step 2 requires calculating the total volume at this point in the titration. The student starts with 0.05 liters of sodium hydroxide and 0.005 liters of hydrobromic acid. The total volume will be 0.055 liters. Step 3 requires calculating the concentration. The concentration of the moles of sodium hydroxide remaining in step 1 divided by the total volume in step 2, so 0.00025 moles divided by 0.055 liters to give us 0.0045 moles per liter. The last step requires converting the concentration of hydroxide into pH using this equation that we covered earlier. Subbing in the relevant values and the pH after 5 milliliters of hydrobromic acid has been added is 11.7. The third part of this question asks for the pH when the equivalence point has been reached. We can work through the same steps as in part B or recognize one crucial fact. The equivalence point is defined by the pH at which the equivalence of acid equals to the equivalence of base. This was described in an earlier video. Since strong acids and strong bases fully dissociate in solution, and the products of the neutralization are sodium ions, bromide ions, and water, the pH at equivalence will be 7. There are no leftover hydroxides or hydrogen ions to alter the pH from its balance at the equivalence point. Great job working through this multi-step problem. Make sure you are systematic when working through the steps to determine the pH at any point in a strong acid, strong base titration. Make sure to follow up this lesson with lots of practice problems.